Thank you, everyone. So my goal here today is help you build your own natural language processing pipeline. The domain I'm going to focus in on healthcare, but we've applied this on emails, on academic papers, on patents, and I've tried to gather the best practices that are common across those. The kind of applications this is good for are applications where it's not necessarily about reading language and answering questions immediately, but usually answering a question about some of the data in the text. So for example, if I need to know, who at the hospital right now needs to be vaccinated for something, the best way to formulate it is as a query. Right? So it's someone who has not been vaccinated before, who is at risk in terms of the department they are in, who is not on chemotherapy, who is not taking other drugs that are conflicting. And those are the people I'm looking for. If I'm looking for people who fit a specific clinical trial, actually the same thing. It's a long set of search criteria that need to be fulfilled. It's people within certain age group, first time with this kind of cancer, have not already started another treatment, do not also have diabetes or some other condition, and that makes them a fit. So in general, with most of these problems, as I'm sure you can tell, there are tens and hundreds of companies working these kind of challenges. Fundamentally, I need to answer queries in a smart, intelligent way. And the challenge is that most of the data that is actually clinically relevant is in free text clinical notes. Okay, so pages and pages of free text notes that doctors, nurses wrote over time, and that's where the data really is. So the question is, how do we get it out? So the first thing we did as an industry, when we had lots of documents and we wanted to get something from them, is we did search. So we had nice query language. We built indexes of text documents, and then you were able to have interesting search queries, and that was so much better than reading the documents one by one, and became popular. And we did it for about 10 years, from the mid-90s forward, and we spent a lot of time talking about how we build robust and scalable text indexing pipelines, how we deal with multiple languages, how do we build different types of analyzers, how we deal with things like spell checking and autocorrect, how we build different rankers, right? So that, for example, if text appeared in the title of the HTML page, it meant it was probably more relevant than it appeared in the text. And we need to deal with different file formats and account for the reputation of the source and so on. So that's one core technology that's in widely used today. That's still not what I would normally consider natural language understanding, because really we're looking at keywords. After that, a lot of progress has been made in specific domains to deal with what's called semantic search. And semantic search means that now you ask me a question and you expect me to understand the intent. So those 5 queries that you see here, I tried them. They actually work fairly well on Google US. And for example, if I'm typing cheap red prom dress, none of these 4 words may actually appear in the text of the product that I'll get as a result, right? But I'll get dresses that are red, which is obviously a fuzzy concept. I'll get dresses that are reasonably priced, and obviously cheap means something very different, if I'm talking about a dress or a car or a camera, right? So it's a category-specific thing. And there's the notion of a prom dress, which is also a very fuzzy concept, which you need some classifier to be able to learn from. Okay, so shopping is one popular category. Anything that relates to context, so things that are happening today, things that are happening in a specific location, this works fairly well. Right, so if I type in, I want NBA scores, or I type in, Super Bowl, I'm getting a result that's relevant for now. There are 2 ways you generally deal with those kinds of challenges within a category. It depends on the category. For some categories, like consumer electronics, you're going to have a fairly good dictionary, so you can have a dictionary of brands, dictionaries of models, dictionaries of the interesting features within that category, right? So you'd expect an algorithm to be able to know just by some basic string parsing that 4K in the laptops category probably relates to the screen, 8GB probably relates to memory, and if it says 512 gigabytes, it probably relates to the SSD drive. And you need to extract this information as you're indexing, as facets, structured facets, and then you need to do the exact same processing when you parse the query, and you send that query and you match. In other categories, like in restaurants and reviews, and this is an actual review from Yelp, you need really more machine-learned annotators of the same kind, because if you're talking about things like, is this a romantic restaurant, or what's the ambience like, what's the value for money, you mostly be looking at examples from what different people said, match it to sort of the review score they gave, and train a classifier that way. And that's semantic search. If you have that kind of problem, you're probably still not in NLP space, but that's the right solution for that problem. Now, usually when people talk about natural language, they're talking about use cases where you really need to understand language. Okay, and healthcare is one example, where if I'm saying, Jen has the flu, Jane does not have the flu, Jane suspects to have the flu, Jane shows flu-like symptoms, Jane is concerned of having the flu. Okay, so whether I'm talking about, whether I'm making a positive statement, a negative statement, a speculative statement, a conditional statement, right? So Jane has the flu, assuming the test confirms. Those are clinically very different things. And if I'm sending those as semantic signals to some machine learning model on top of it, it better be the correct signal. Okay, so there, anything that you have here that is related to just matching strings, matching keywords will be completely useless. Okay, and what's happening in healthcare is that usually the more important something is, the more useless a keyword-based approach would be. Okay, because for example, usually it's very important to know whether someone is diabetic, someone is overweight, someone has a heart condition, the most common conditions, right? So that's why what you and I will get asked about when we go into a hospital. But the thing is, like, the word diabetes probably appears in the clinical record of all of us. Okay, even if you're not diabetic, because we tested negative for it, because someone asked us about it, because they actually had to check in with us every other year or so. Definitely, if you're within a hospital, within a specialty, right? So if you come in pregnant, right? If you come in for a specific surgery, right? There's the standard set of things that everybody asks you about. So if you don't know whether this is positive, negative, speculative, patient history or family history, which you can only know by understanding grammar, you have very little you can use going forward. So those are the kind of problems we're talking about. And there are three things I want to make sure I get across. This is the first one. First one, if you have a problem that really is a language problem, where you really need to understand human language, it gets complex very quickly, and it gets domain-specific very quickly. So very much like semantic search, I can tell you, so things we've built here for healthcare will only work for healthcare from these specific sources. And most likely, you'll need to build specific, you need to write specific code, train specific models for the domain you're working with. So here's one example. Joe expressed concern about the risk of bird flu. So Joe does not have flu, he does not have flu, he does not maybe have flu, there's just nothing going on. Okay, and to do that, you need to understand that, yes, some human statements are just speculative, or this is how you express these. You need to be able to deal with the compound sentences. You need to be able to deal with double negation. You definitely need to deal with irony and all the different ways people use to express things. I can tell you that within 3 months of starting to work on this, we had over 100 ways to say that a patient does not have something, and we're still adding. We work with other companies. I work with another company that's been doing this for 7 years and say, yes, they still find new ways for people within the subspecialty of radiology to say the exact same thing in different ways. So there's a lot of richness in human language. And you're never going to be done basically understanding human grammar, which is pretty amazing academically, pretty frustrating when you're trying to sell this. The other thing that you need to know that you really need to understand a specific domain. Okay, so for example, a patient denies alcohol abuse. So can anyone guess, what does a doctor mean when they write that? Okay, so, exactly. The only reason for a doctor to write patient denies alcohol abuse is what they mean is, I suspect alcohol abuse. Okay, meaning if this person, when they actually get into the hospital, like, please do not kill them by giving them, that kind of medication that interacts badly with alcohol. Okay, even though they deny it, which is textbook. Okay, and this is something that you'll only be able to know if you are within the subdomain of substance abuse, right? And you understand the context in which someone would write this, right? And the context in which someone else would read this and use this information. Okay, similarly, when you're writing, allergies, colon, penicillin, comma, dust, comma, sneezing, we are not saying that the patient is allergic to sneezing, right? We are also not saying that the penicillin causes the sneezing, right? Because there's just clinically, that's not how it works. Okay, and a lot of it you only know really, and once you're in that domain. So those are some examples, but really, Those are the easiest examples, because typically what we see is that in clinical records, about half of the sentences are just not valid sentences in English. Okay, like they don't have a subject and a verb and what everything relates to. Okay, people just don't write that way. Mostly it's because they don't write. Most of the time they speak it. Okay, and there are codes and there's a lot of jargon people use. Okay, and in general, what we've learned is even so the things that you'd expect to be able to get off the shelf, like sentence detection, where does a sentence end, where does a paragraph end, so the simplest things you want. Okay, because if you're reading SMS or text messages, okay, well, you're definitely not going to have punctuation, right, and it has its own grammar. Okay, and on the other end, if you're reading academic paper, right, then you'll definitely have complete sentences, and most of the time they are edited, and you have fairly good language in terms of just the grammar correctness of the language. When you deal with open source packages, for example, if you take NLTK, most of the models that come with it are trained on Wall Street Journal articles, which, for this, I mean, it's almost the worst, because newspaper articles, they're professionally written, professionally edited before they get published. Okay, so, very good, proper English. Okay, and, in a few domains, for example, if you're analyzing tweets, it's completely useless, right? It's a different language, different vocabulary, different grammar, right? You really need to train on different kind of language. So that's one thing you really need to be aware of. So what comes with this talk is a set of notebooks that are free, and the last slide has the location on GitHub, and the goal is for you, if you're interested, just download the notebooks, play with the code, and start from there. Here's the architecture of the whole thing. So the data set we use is what's called the Mimic3 data set. It's a set of a publicly available set of clinical notes. About 100,000 people went to an ER in Boston, actually, right here. It's anonymized. You do need to sign a privacy agreement, meaning that you promise you will not re-identify this data, but otherwise it's free for you to download and use. The actual processing, so actually adding the annotation to the text, is done on top of Spark, and on top of that on UEMA, and we'll talk a bit more about UEMA on the next slide. And then once we're done with that, we generate assertions. Okay, and assertions basically mean a structured record that says, look, yes, we think that this patient has a symptom of broken finger, right, and this is why they came today, right, so this is not history, this is current. Okay, and these are signals that you can send to UI or to, most commonly, to machine learning algorithm. And we put them in two places. And usually, you need to show those kinds of assertions or deductions you made in two places. One of them is in an interactive queryable interface. So here we use Elasticsearch. And the goal is really for people to be able to understand what deductions you made and why, and correct them if they need to. The other one is more for batch analytics store where you can run training, and we use Spark and Spark SQL for that. So you have a set of notebooks that actually makes this happen. I want to talk a little bit about UEMA. So UEMA is an Apache project. It's been out for a while. It's a fairly mature framework to build annotator for natural language processing pipelines. It's a Java framework. Each annotator is a Java class. And an annotation means that I made some deduction from the text. Simple deductions are, for example, I match the word to a dictionary. Right, so you have the word flu, and I match it. Yes, this is the name of a disease. Okay, that's a simple annotation. And then other annotators can use either other pieces of the text or also build on other annotators. Right, so for example, I can have an annotation that only uses other annotators and says, okay, this patient has this disease at this time frame. Okay, and then on top of that, you can have more semantically advanced annotators. For example, to come and say, look, this happened to the patient, and then later on this happened, right? So things like before and after or cause and effect, okay, that you deduce by language. And what UEMA does is really it runs those annotators basically until all possible deductions have been made in an efficient way, and gives you the result, and also comes with some nice tools, some UI tools and debugging tools to be able to do it. As I mentioned, one of the things we found out that we need to do, and one of the things you need to plan to do if you're running this project, is you'll need to build most of the annotators on your own. And I can tell you, we've used every open source and commercial, sentence detection, negation detection, dictionary matching library that's there, and very quickly ended up building our own because there were always some fairly basic use cases that did not work. And it was the same when we worked on clinical records, it was the same when we work on patents, the same when we work on emails. And this is just something that you need to plan for. It's a domain-specific problem that you need to implement. These are some examples from the notebooks, so you can see the actual notations. It deduces polarity, it uses the subject of the sentence. You can look at the assertions, you can visualize them. There's a whole set, there's about 30 dictionaries that are being used, so different types of inferences, so we can do symptoms, procedures, allergies, medical devices, lots of medically related things that could happen to you. It's a long list. And you're welcome to look at the code and start there. So as I said, the first thing you need to do is really just assume your project is going to be, it's a domain-specific problem you need to solve. And the basic tool that you need is some kind of annotations pipeline you can work with. The next thing to point is you'll be doing machine learning really mostly from day one. So far, it looks like, yes, just building an annotator, I'm doing keyword matching, I'm learning the grammar, where does machine learning fit in? But actually, if you look at any natural language processing library, half the documentation is going to be how do you train and measure your models. And because most of the models in real human language are fuzzy, which means really that it's easier to learn them from examples, actually specify the rules. So here are some basic examples where you can actually think about coding the rule. So yeah, if then in language, I can write it as one example. If your age is under 18, you're a child, yes, you can mostly code that. And you have some of those examples. But in most cases, it's much easier to learn the things that are relevant from examples, meaning train a machine learning algorithm. So one example that's very popular in healthcare is underdiagnosed conditions. Okay, so for example, depression is often underdiagnosed. Okay, so you're going to have very few cases where someone actually went to a psychiatrist and they're actually positive diagnosed for depression. The same thing with the flu, by the way. I'm sure all of us have had the flu. Far fewer of us actually went to a doctor, and far fewer of us actually did the test and got a positive diagnosis, because most of you just stay home and drink tea, which has the same impact. So if the question is, okay, how many people with depression do we actually have? Or how many people with the flu are actually in the hospital? You need to look at other clues, right? You need to look at people who seem to have the same symptoms. Okay, and that's a classic machine learning problem. Another thing that happens very often in every domain is that when you're working with the text, if I'm explaining things to you, there are a lot of things I'm not saying because they're implied. Okay, so in healthcare, one of my favorite sentences, relevant labs normal. Okay, relevant labs normal, that's a sentence. Okay, so first of all, you need to figure that's an actual sentence. Now, of course, it means not only it means different things for different subspecialties, it means different things within different floors of the same hospital, right? I mean, it's a very, very localized thing, right? It's because the way, if we have 10 beds in a hospital and we deliver babies, right? Then it's going to be, 8 doctors and 15 nurses working together for 5 years. They're going to have their own language, their own jargon, their own understanding. Okay, and they're going to be very quick about what they're writing because everybody's busy. Okay, which means that you need to learn localized models, very localized models, to really understand, break into the jargon of that group of people. And that's a machine learning aspect. The example that's in the notebooks you have here is something that you think would be simple. The question is, here's a medical record, is the patient a man or a woman? Okay, which turns out to be very hard to explain via hard rules. Okay, so sometimes it just says in the text, patient is a 5-year-old male, blah, blah. Sometimes it just says he or she. But very often he or she depends to family members, depends to, talks about the doctor, talks about the baby who was just born, and you're actually fairly bounded by the accuracy you can reach unless you use a machine learned approach. And there's just one example of really a very, very basic clinically relevant concept that you need to be able to deduce. And we've seen this in other categories as well, other domains, that really in the vast majority of cases, the interesting annotations, interesting deductions from the case will be machine learned. The third and last thing I want to bring across is really how you deal with your vocabulary. And in every domain, you're going to have your own unique vocabulary. In healthcare specifically, it's very unique in the sense it's easy. Taxonomies and ontologies, in general, human history, started with biology, right, with Darwin and before that. And medicine is actually one of the few areas where humans for hundreds of years have cataloged all the bones in our body and all different body parts and all the diseases and all the things that could kill us and go wrong with us. So actually, medicine is one of the few domains where you actually have a good taxonomy and ontology to start with, an excellent one that people use and work with. If you're studying politicians, If you're studying movies, if you're studying music, okay, if you're studying current events, if you're studying commercial companies and acquisitions, you're going to have nothing of the sort, right? So yes, you'll start with a baseline, right? Or you can curate a small starting point, but you'll have a much bigger problem of both having a full set of taxonomies, and this is really for the basic problem of, if I see the word flu in a text, I need to know it's a disease, right? So if I see a word in a text, I need to know that this is actually the name of a politician or the name of a person, the name of a company I work with. You'll need to find a way to build that list in a comprehensive way, and more importantly, keep it up to date. And we have seen this in healthcare as well, where the problem of expanding the ontology mostly to learn jargon and keep it up to date is a problem. The example you have here is using Word2Vec to do just that. So that's an example in a notebook that's been provided. And Word2Vec is, it works decently well within a domain if you have a large number of cases to learn a subspecialty or learn a relationship between concepts within a limited space of documents. Okay, so the main thing you need to make sure you do is that within the set of documents you pick, make sure the grammar is similar. Okay, so don't mix newspaper articles with academic papers with emails, okay, because we have a very different grammar, and that the vocabulary is similar. So within healthcare it means don't mix cardiology and oncology, okay, and make sure that there's similarity within the subset of documents that you're processing. The implementation that we use in the example notebooks is just the Spark MLib implementation of Word2Vec, right? So it's completely free, completely open source. I would say internally we've gone beyond it, but we want to make sure we have something that people can just go and use freely. So that's what we have. We train with the same mimic3 dataset, okay? But now we use those clinical records really just as a training set, right? So we notice something that we want to annotate one by one. We run it through Spark MLib, and we use it to update the ontology. So this code basically takes the original UMLS ontology, which is the most public version of, curated public version of medical ontologies that's available to you, and runs the updates. Okay, and then once you've updated the ontology, basically you use it back in step one, in the step we saw before, where really your basic annotators will really try to do word matching to have the most basic level of annotators, right? To kind of say, okay, this is a disease, this is a drug, this is a procedure. It can work correctly. The main thing to know about, let's see how we're doing well with time. The main thing to know about using Word2Vec is that it works in the sense that you are going to get semantically relevant, semantically similar concepts, but it tells you nothing about how they are similar. Okay, so you could get spelling mistakes is very often happens a lot with diseases. You have 15-word letters that people argue about how they're supposed to be spelled anyway. So really you want to get all different spellings. Sometimes it's going to be drugs that are often treated often used for the same disease, right? So you'd have those links between the drugs. Here you have some example of link between, mostly between drugs and some links between diseases. Okay, so it could be a relevant disease, it could be a relevant drug. So what you cannot do, okay, you cannot assume that because this thing told you that those are semantically relevant, that they are not synonyms at all. Okay, they might be, but they usually are not. They are not the same concept. They may not even be from the same family of concepts. Okay, so just make sure you do not make that mistake. What you can use them for is definitely you can use it for signals for machine learning algorithms. Okay, so if you know that the fact that someone takes a specific drug, okay, is a strong signal for bleeding, complication, better recovery, whatever may be the case. Okay, so if you don't have that specific drug, but you have other words that are semantically very close, okay, in a sense, you don't care if it's another drug that's closely related or if it's actually a disease, the disease that this drug is given for, right? You just want to know, look, it's probably semantically the same thing, okay? So even though they do not mention the drug name, you can go and make that assumption. The only way you test if you're actually adding value and not adding noise is you actually want to do the measurement on the machine learning algorithm that's running on top of this. But we have seen that in very common cases, yes, you are going to get a lift and you're going to get better accuracy because it's fairly rare that people write the same exact drug name and actually write it in the note where you need it and not just kind of say, the patient uses standard treatment for blah. Okay, so that's the only thing, and obviously there's a much richer set there. So just to summarize, whatever domain you're working on, 3 things to know. First of all, you want to find if you actually have a natural language problem, right? So the question is, do you really need to understand grammar, or are you okay with just analyzing keywords? And then you're in a simpler place. If you do, assuming you need to spend continuously a long time on just understanding human language, do not assume you'll be able to find off-the-shelf stuff, not commercially, not open source, because you'll need to learn your own vocabulary, your own grammar for your use case. Assume that you'll be doing a lot of machine learning early on, at least for the things that work in a reasonable, it's almost always machine learning models that run, they actually do the annotations, and make sure that you have some mechanism to both build and then, very importantly, keep your ontologies and dictionaries updated as you go. Okay, if we have another minute or two, I'll take questions.
We're open to questions. I got Mike here.
Okay.
So feel free to ask questions. Okay.
In the case of the medical UMLS, I think, was that a human-curated ontology?
Yes. So UMLS is the human-curated ontology. It's the unified medical language system. It's a collection of, I think, just in English, they have something like 110 different ontologies. And basically what they've done, they take it from the organization who curate them, put them all in one format, and you can download it really as one thing, which is free for use.
If you're starting in a domain where you don't have an existing human-curated ontology like that, what do you think the role or interaction between a machine-derived ontology and then human curation? What's that interaction like?
Yes. So I think it heavily depends on the domain. So if you have a domain like, for example, like consumer electronics, probably the easiest thing is you can sit someone for 2 weeks, and they can give you pretty much full lists of all the brands, main brands of laptops and cameras and the models and so on. And then it's just really the cheapest and fastest thing to do is just to sit someone to do it in a manual curation kind of way. If you're dealing with people, okay, and you need to know the current nickname of every celebrity that you're tracking, okay, then the easiest thing to do would be now you probably want to crawl web documents and apply something like Word2Vec or similar network, because then it's probably something you want to run 3 times a week to get updated results, right? So I think it heavily depends on the domain, really how fast it changes and how much training data you can get to bootstrap.
Great. Any other questions? Yeah. I have one follow-up question.
Sure.
So can you comment on what made you decide to use Spark as opposed to any other tools?
Sure. So let's see. When we started, it's 2012. I think we're still on Hadoop and MapReduce at the time. And we started with Spark actually very early on. I keep saying we started with Spark when it was not working yet. And went on with that. And it's definitely a much more mature space now. I think the main thing was really just, for us, it was a combination of performance when we need to run this at scale with just the developer productivity, right? Because a lot of the examples and training you do on your laptop, right? You need to train things on a subdomain, and those are just things you do in memory. But then, when you go to a customer and they have 10 million documents and you need to process them, you need to have that scale as well. So for us, being able to do both was for us enough to try Spark early on and go with it.
How do you measure the performance? Like when you go work with some customers, a lot of this are really unknown, right?
Yes.
How do you measure them?
Yes. Yeah. So that's an excellent question, because there are a lot of traps you need to be aware not to fall in. On the language itself, sometimes we had our own labelers and our own judges to look at specific models. Okay, how good are we at finding out what's like specific conditions, specific codes that are happening. With customer, often what they would care about is really the machine learning algorithm that's on top of the language. Okay, so for example, if you are trying to match people to clinical trials, or we're trying to give the most relevant medical paper for a patient, then that's really what they want, and then that's really what we want to measure with them. Yeah.
Okay.
One thing you should know, especially when you're talking to business customers on this, because the models here that you build are so localized, right, or so domain specific, they do not transfer well. Okay, so one of the things that are basically a complete sales fabrication, right, is to come and say, oh, we have this working perfectly on cardiology. Of course, we can run it next week on, on pathology. Okay, well, the reality is, we've seen cases even within the same specialty. We move from one client to another. We go from 95% accuracy to 5% accuracy. Okay, like basically, you have nothing working at all, even the most basic use cases. So that's one thing to be aware of in terms of measurement. You need to make sure your customers understand what the measurements relate to. Yes.
My question is about the mimic data set you used.
Yep.
Does it contain any demographic information of patients? If it does, I know there's a PHI issue, but that's not really the question. The question is, when you build the dictionary, do you put the demographic information in the dictionary or not?
Yes.
Thanks.
So Mimic gives you some very basic information, gender, age, and some previous diagnosis. In general, look, the age and the gender of a person are clinically extremely relevant. Right? So to know whether your patient is 6 months old or 96 years old, right, whether male or female, obviously impacts a great deal on what deductions you will make. So yes, we do use this information. Look, I would say in general, the way you want to build machine learning algorithms, look, I'll use whatever information you give me. Right? So language is usually about 80% of the information you need. But other than that, age and gender, you very often have in structured fields. Drugs, like what drugs people are taking, what prescriptions you have that you can get, we use whatever we can get.
So if that's the case, then if you also have names, especially first names, right, they contain clues as to the gender. So,
yes.
you also use that information.
Well, so the Mimic dataset does not have names. It's an anonymized dataset. Here's the challenge here. If you have datasets that have them, okay, so let's say, for example, you're dealing with social media data or other data, you can keep the names. So yes, the names can be a good hint of gender. They can be a good hint of even where you live, right? The challenge is with things like names, because there's a very long tail of names, you stand the risk of overfitting. Right? So if you just train a model, there may be, look, there were 2 people with a specific name, right? If your model deduces that all those people probably live in this area of Brazil. Right? So you need to, when in general, when you use features with long tails, overfitting is a concern. Right.
Interesting. So our next speaker should be Kishan Farhi, but I don't see him. Oh, correct.
Okay, thank you.
Come on. Thanks so much.